belated Eid Mubarak to our Muslim brothers and sisters. Eid Mubarak, okay? All right? Okay, because I noticed you guys weren't here, eh? I noticed. Matrix multiplication. That's where we are. All right, come. So, guys, you finished chapter 1 and chapter 2. We're jumping to chapter 4, and then we're going back to chapter 3, or sections. You don't have to call them chapters. Okay? So we're going to do matrix multiplication in order to do transformations. Okay. When we multiply two matrices together, we get a new matrix. But the size of the matrix is important the size of the matrix is important because you cannot multiply certain matrices together. And I'll show you how we do that. Okay, so we're going to multiply two matrices together to get a new matrix. All right? C. So when we multiply, matrices, we take we'd say a row in the first matrix and multiply the corresponding entries. Are they corresponding? Yes, the corresponding entries of a column. Now, be careful this. We're taking a row here and we're multiplying it with the corresponding entries in the column. So I'll illustrate it just now. In the second matrix. And that's how we do matrix multiplication. And add them together. So basically, in general, this is a simple example. If we have A, B, C, D, E, F, G, H. All right? Two matrices that we are multiplying together. What we do, we take the entries in the first row and multiply it with the entries in the first column to get the first value would be A times E at the back. A times E plus B times G. All right? So it's this one, that one. So it's A times E, right? B times G plus B times G. And that's one value. That's one value you get. Okay? The second entry, maybe I run out of space. Where's my board dusters? Anybody see my board dusters? They're not here today. Okay. We're going to have a short lecture. The next one, so this is the first entry. We take the first row and then the second column for the second entry here. All right? So what do you expect? AF plus BH. AF plus BH. Then we do the next row. The same procedure. Let's do another color. So we're going across and down. We go across and down when we do matrix multiplication. CE plus DG. All right? And the other one is CF plus DH. So we're going across and down. All right? All right. Now, this works nicely. This is a 2 by 2 matrix. This is a 2 by 2 matrix. The idea is that how many columns there are in here must correspond to how many rows in here. Okay? So these two values must be the same. Okay? I'll write it out. The number of columns in the first matrix must be equal to the number of rows in the second matrix. Because if we had another value here, just say another here, another row here, there's nothing to multiply it with. So the size, as I said, the size is important, but what we mean is that the number of columns in the first matrix must equal the number of rows in the second. Okay. All right? So, let's see if we can do the following. Right? If we have 1, 2, 3, 4, 5, and 6, can we do this one? Can we? Yes, we can. Okay, let's look at the size of this. So this has 2 columns, right? And this is a 2 by 1. How many rows? By columns. That's how we talk about it. We talked about this yesterday, how we talk about it. So these are the rows, these are the columns, right? So it's a 2 by 2 matrix here. 2 rows, 2 columns. Here we have 2 rows, 1 column. So these two are equal. So we can. So then what is I end up, watch this, I end up with this many matrices, a 2 by 1. This is end up. So I'm expecting a 2 by 1 matrix. Okay? Some of you have done this in school, not everyone, so just hang in there. So it's 1 times 5 plus 2 times 6. So it's 12 plus 5 is 17. Yes? And then 3 times 5, 15 plus 24. 15 plus 24, 39. Okay? Are you happy? Any questions now? So it's across and down, across and down. So we end up with a 2 by 1 matrix. Let's do another example. What about if we start off like this? Can we do that one? Think about it. I'm going across and down. No. Because what is this? This is a 2 by 1, and this is a 2 by 2. These two are not equal. Huh? No. Because they asked you to multiply it this way. So yes, the only way it can work is if it was on the other side. But that means A times B does not equal to B times A. All right? If you are given matrices and you're told to multiply it like this, there's no answer. Right? So cannot multiply these two in this order. Okay, simply doesn't mean I can just change it over to that side. If the question is saying multiply these two together, we answer the question like that. They're saying that times that. If they had said the other way, this times this, then you can. Right? Question at the back? Yes. Okay. We'll do an example just now. Okay, let's just check. Yeah? Okay, so he's asked a very nice question. It was linked to the question yesterday. An augmented matrix is derived from a system of linear equations. So that line there really means equal to. So when we are doing something with it, we are solving it. All right? Here we have a matrix on its own. And we'll see maybe we'll get to it today or maybe tomorrow, that when you do something, just say this was a point, okay? This is a point, you can write it as x and y, right? If we multiply that point, we are doing something to that matrix. So if this was just x and y, we could change or transform a point to another point. And we'll do that just now, okay? We'll do it. We'll see how far we get today. Yeah, maybe we will. We will, okay? We'll see how far we get. But basically, we talked about matrices being an operation. It's like an addition or a subtraction. It does something to something, all right? And we'll see it now when we do linear transformations, okay? All right. The other idea is that actually we can write the augmented matrix in a different way. We can write it as normal matrices, okay? So we started, and this is going to help us when we find the inverses of matrix. So everything is linked. If we have a matrix A and we multiply it by a column vector, we get another column vector B. Now this is, remember when we could take a system of linear equations, put it into an augmented matrix, and then say, but if we rewrote it, what would it mean? Okay? So I'm going to write it all down. A11 x1 plus A12 x2 plus A13 x3 equal to B1. All right? This is the system of linear equations that we're going to make look like that. Okay? So we can say since, all right, we get these linear equations, 21x1 plus A22x2 plus A23x3 equal to B2. and A31x1 plus A32x2 plus A33x3 equal to B3. Now we wrote it as the augmented matrix where we took out the coefficients. Sorry. A21, A231, A12, A22, A32. We took out the coefficients like that. 1, 3, 1, 3, 2, 3, 8. And we put it into an augmented matrix like that. Didn't we? So we took the linear equations when we could convert it to an augmented matrix. This is just a reminder, right? We could do that. We can also do something else. But it depends on whether we can find a duster today. Anybody see it? Am I blind here? The duster, the board duster. Ah. Okay. It's not in here. Okay, I'll be back. Have fun. Is there something happening in here?
I'm meant to give a lecture. I can't remember which venue and my computer's not working.
Let's see if there's somebody in here. Maybe. I'm just going to see if you've got extra board dusters, because my room. Okay, I'll return it just now. There's no board dusters. Okay, shh. So now we can also write the augmented matrix. Watch this, guys. Guys, we can also write, so you can write here, we can also write it as your first, all your coefficients in this one, A12, A13, A21, A22, A23, A31, A32, A33. Now think about it. Do we get that system of linear equations if we do it like that? We are saying we're going to get A11 times x1 plus A12 times x2 plus A13 times x3 is equal to B1. Do we get the first line? So yes, we could write it as this now. Okay, and since we know how to do matrix multiplication, this is a 3 by 3, this is a 3 by 1. Can you see these two are equal? We can multiply together, and we end up with a 3 by 1, which is what we got. Okay, so it's just another way of writing. It's going to be useful when we are doing inverses a little later on this week. All right. Now, linear mapping and transformations. So we're going to start it today. Yes, sorry?
Does this format have a name? Like down as augmented matrix? Does this one have
It's just matrix multiplication. Okay? But, yeah, when we're doing linear mapping and transformations, you'll see now that actually we can change a space. We can make something look different. We can change the space. We can transform it. So we start the section, linear mapping and transformations. Okay, now, if you had, right, if you had a system of 3 linear equations with 3 variables, you could geometrically think of it as 3 planes. Yes? Say it again. If we had 3 equations with 3 unknowns, all right, we could say it's x, y, and z. We could think of it as 3 planes where they intersect if we had to solve that set of linear equations. So if we had 2y minus z equal to 2, 2x plus y minus z equal to 1, and 2x plus 5y minus 3z equal to 5. I've already done this. We Gauss reduced this to solve the system. Oh, we Gauss reduced. Didn't have to say this. We Gauss reduce to solve the system of linear equations. And my answer, when I Gauss reduced, which is the correct answer, and you guys can do it if you want to, right? And we got, okay, so I'm telling you what the answer is, right? We got a line. So we got infinitely, or we should say, we got infinitely many solutions, or a line in R3, right? When we talk about R3, it means 3 dimensions. Yes, you know that. Okay? All right? So that means our solution that we got, so we got, you have to trust me on this one unless you want to do the Gauss reduction. We got 0, 1, 0 plus lambda 1, 2, 4. Okay? Lambda is an element of R. All right, what that means, if we have to rethink this, is that if we take that matrix, if we took that matrix, this matrix, and took the coefficients of this on the left-hand side of the equal signs, so we put it into a matrix. So then, just by using what we learned over there, oh, it's already erased, we could say that the matrix A was going to be 0, 2, minus 1, 2, 1, and minus 1, 2, what is that, a 5? 5 and minus 3 when multiplied by x, y. Oh, okay, we want to say when act on a point any point on this line. So this is our matrix. This is any point on the line we found. Okay? Any point on this line, it should give us 215. All right? So can you give me a point on that line? 0, 1, 0. Let's see if we get 215. That times that, plus that times that, plus that times that. What do you get? That times that is 0, 1, 0. That times that. You can see it? So we got 215. All right. Okay, so we get okay, let me write this. If we multiply A, or rather, I don't want to say that. Sorry, guys. I want to say if we let matrix A act upon any point on the line and our line was this one. This is your line. We get 215, the point 215. So basically, we are transferring all the points on that line. If we apply matrix A and it maps it, watch my language, it maps all those points on the line onto a single point. Isn't that cool? It's taking a line in 3 dimensions and putting it onto a point. So all those values on that infinite line, they map onto 215. Okay? Let's just take some more points on that line. Do we get 215? Yeah? So this, when we talk about linear mapping and transformations, it means we are applying a matrix, letting it act upon something, and it results in something else. Okay? So it's like an operation. You're doing something to something, and it's like, this is the new thing. Okay? So what has happened here? We let matrix A act upon any point on that line, and we get back to 215. That was just one point. Let's take a couple more on that line, and then you can be convinced. All right, so can you give me a couple more points on the line? This is 0, 2, 2, 2, 1, 5, minus 1, minus 1, minus 3. Another point on this line. 1, 3, and 4. So we let lambda is equal to 1. Shh. What do you get? 2 times 3 is 6. Minus 4 is 6 minus 4. All right, is 2. Then we've got 2 plus 3, which is 5, minus 4 is 1. And then that's 2 plus 15, which is 17, minus 12. Isn't that cool? Wow. Okay, any value for lambda, put it in there. Even if it's, hey? When we made lambda equal to what? Ln E. What is ln E, guys? There we go. All right? Shh. Are you convinced, or must I do some more? Maybe make it 1,000. Hey? Put fractions in. Make my life difficult. Okay, you're going to do the calculation in your head then. All right. Shh. Yeah? Sorry? Yeah.
But in this sense,
so in this format, this is a point in 3 dimensions, right? X, Y, and Z. And this one as well is a point in R3. Both of them would be points. So basically, we rewrote, before we Gauss reduced it, all right? We got a line. So we are saying this is a solution line. So if we applied this solution, we'd get these values.
yeah, because it's like every point in that in your input, your parametric equation, and then to one side. So why is it?
Not every point. Not every point. Every point on this line, on the solution line that we got, gets mapped onto 1.215. Okay? X is 2, Y is 1, and Z is 5. So we... No. We're taking a point, right? Just say you got, this is 3 dimensions, right? We've got a line which is our solution. What happens is we apply that matrix A onto it. Let it act. What it does, it acts like a black box. It takes every point on that line, those infinitely many points on that line, and it mapped it onto a point separate to that line, 215. Okay? All right? So basically that's what it's doing. It's mapping it onto something. Shh. Guys. One more thing. Shh. So what yeah. So I'm going to write something here. Please copy it down. So I'm just basically writing what I said just now. A matrix can be seen as a function or operation, right? It's doing something, right, to something to make it something else. So it's like a function, all right? Or operation. Can we sing or operation? Operator. Maybe it's an operator, okay? It takes a point in space. We mean either R2 in 2 dimensions or R3, right? We will be looking at R2 just now in more detail, and sends it to another point in another space. Sometimes the operator can map a 3D point into a 2D space. Okay, so we just have to be careful. In another space, in R2 or R3, it depends on your size of your operator. This is known as linear mapping. Or transforming one space to another. Okay. Now, in our syllabus, we will look at, yes, we can do linear mappings using a 3x3 matrix to do an operation onto a point. Yes, we can do it, but for simplicity's sake, we are going to look at only 2 dimensions, okay, for just this syllabus. Okay, so we're going to look at transformations in 2 dimensions only. Okay, we're going to be looking at transformations in 2 dimensions. Basically, the idea is we're getting a transformation, whatever that transformation is, we're applying it to a point in, so we call it our old point, and we're going to get a new point. All right? So that's the easy stuff we're doing. So it's AX plus BY would be your X, new X coordinate, and CX plus DY would be your new Y coordinate. Okay, so let's see. We're going to look at something, and I'm going to give it a heading just now after we do the presentation, so leave a space. What does this matrix do? What does it do? So we think about it. Maybe I'll do the first one for you. So we've got a point, general point in 2D, and we apply this matrix, and what do we get? 0 and y. That means any point on your Cartesian plane, xy, is mapped onto the point 0y. What is 0y? It's the y-axis. Yes? The point 0y. Oh, I love when the penny drops. There's your x and your y. We're just doing 2D. Okay? Are you all right? Not today. So I took the flu medicine and you getting all the side effects. All right. So we're taking any point. Shh. This is a general point, x, y. And it gets onto that point. It's keeping the y value. So what is it? It's mapping it onto the y-axis. All right, can you see this point is 0 and y, right? Okay, so we call this the projection onto the y-axis is that operation. 0, 0, 0, 1. That's the operation that changes any point in 2D to that corresponding y entry on the y-axis. All right, so it maps it onto the y-axis. So we'll give that a name. Ish, I can't even reach. Projections. All right. Sorry, this bullet belongs to this guy. Projections. What does, so there's your question. What does that do? Okay, that's good. All right, so now you can help me do the rest of these.